Now we'll consider the temperature dependence of the rate constant. There's a simple equation that gives a rate constant and its functional dependence on temperature, and it's called the Arrhenius equation, and it states that K, the rate constant, I don't have enough room here, I'm going to write it down here. K is equal to A, what's called a pre-exponential factor, and E, the base of natural logs, and to a power we have E sub A over RT. Now let's talk about what these things mean. K is the rate constant that we've seen before. A is called a pre-exponential factor, or sometimes called the frequency factor, and it has to do with the probability that a collision will result in a chemical reaction. And then we have E sub A here in the exponent. This is called the activation energy for the reaction. R is the ideal gas constant, and T is the temperature. Now let's pictorially see what the activation energy means. We'll have energy on this scale and a reaction coordinate on the horizontal scale. You don't really need to know much about it, but let's look at the energy differences between reactants and products. So we'll start here with reactant and we'll end up here with product. Now we have to go through an energy barrier most of the time for reaction to happen, and so we have to go up in energy, and this barrier is called the activation energy, and it's the distance in energy between the reactant and what's called a transition state. And the transition state is at the very top of the barrier. Now if a reaction has a large activation energy, that means it has a large barrier to overcome in order to react to give us products. If it has a very low activation energy, then it has a low barrier. So this is temperature dependent, because if molecules have a high temperature, they have a higher kinetic energy, and so when they collide with more energy, and that collision can result more probably in a reaction if the reaction mixture is hot, because more molecules have enough energy to get over the activation energy barrier. If we have a very low temperature, just a small fraction of molecules might have enough energy to overcome the barrier, therefore the reaction occurs very slow. So at high temperatures, the rate constant is larger. At low temperatures, it's smaller. It follows the Arrhenius equation. There are a few exceptions, but most reactions follow this type of equation. Okay, I'll rewrite the Arrhenius equation and see what we can do with it. So, if we know the activation barrier, E, and we know the temperature, and we know the frequency factor, we can determine the rate constant K. One thing that's interesting to do experimentally is to find the rate constant at several temperatures. And when we do this, we can take a ratio of rate constants. Say we know the ratio of the rate constant at temperature 2, and we'll divide that by the rate constant at temperature 1. So the only differences here are the temperatures. So I'll put T2 with K2 and T1 with K1. I'm taking the algebraic ratio, so you notice first off that A, the frequency factor, cancels, and so we can write the ratio. I'm going to combine the exponential terms into one power. Now, use the fact that e to the a times e to the b is equal to e to the a plus b. Okay, now I can take the natural log of both sides of the equation. I have the natural log of the ratio of the rate constants, and since I'm taking the natural log of which has base e, the right side of the equation will just be the powers. And I'll factor out on the right side of the equation minus EA over R, and it will give me this difference in the inverse of the temperatures. So it will give me this equation, which is important, and this just tells me that if I take the ratio of the rate constants and the natural log of that, it's equal to the right side of the equation. So now I have the activation barrier and the temperatures out of the exponent, so I can solve for them if I want to. So knowing the ratio of the rate constants, I can solve for the activation barrier or the temperature for one of the rate constants. Let's solve for the activation barrier. So E sub A is equal to minus R times this factor. Now you'll see that I've divided through by the difference in the inverse temperatures, and so I've written the power -1 to show that I've divided through by that factor. And then I have that multiplied by the natural log of K2 over K1, the ratio of the rate constants. So knowing the two rate constants and the two temperatures, I can find the activation barrier. Now say I know the activation barrier, E sub A, and K1, T1, and T2. And I want to find, say, the rate constant at T2. So I can solve for that. So the natural log of K2 is equal to the natural log of K1 minus E sub A over R times this temperature factor. Just algebraically solving for natural log of K2. So now I can take the analog of both sides of the equation and get a value for K2. So it'll be K1 E So there are 5 things in this equation. There's K1, K2, T1, T2, and the activation energy. Knowing any 4 of these, I can solve for the 5th using this equation that is boxed in above us.